you for the organizers for inviting me. So today I'm going to talk about cohesive powers of various kinds of structures, in particular algebraic number fields. But just as a review of some classical model theory, so in classical model theory there's the notion of an ultrafilter. So it's a family of sets closed under finite intersections and supersets, and such that any set or its complement is contained in the ultrafilter. And this is a largeness notion, and the only interesting ultrafilters are the non-principal ones. But we don't really know if non-principal ultrafilters exist, so they're a consequence of the axiom of choice, weaker than full choice, but stronger than choice for finite sets. So it's equivalent to a certain level of choice to assert that every non-empty set has a non-principal ultrafilter. And using ultrafilters, we do the ultrapower construction. So we start off with a structure, and we take its Cartesian power, the set of all functions from the index set to the structure, and then we take a non-principal ultrafilter on the index set, and then we define an equivalence relation based on the set of indices being large in the sense of the ultrafilter, and then we form a quotient structure using that Cartesian power over that equivalence relation in the straightforward way. So constants map to the constant function, functions map in the straightforward way, and a relation is true if it's true on a large set of indices. And then we have Wosch's theorem, which says that any ultrapower is a model, is elementarily equivalent to the original structure. And so examples of ultrapowers are well known. So for n, you get the hypernaturals. For r, you get the hyperreals, and so on. But all these constructions are often uncountable, and they're always non-constructive. And so depending on your philosophy of mathematics, that might make you uncomfortable. So how do we make me comfortable? Because that's the goal, right? Make me comfortable. So we have a computability-theoretic analog of the ultrafilter known as a cohesive set. So a set of natural numbers is cohesive if it cannot be split in half by any computably enumerable set. In other words, any Turing machine either outputs only finitely many elements of the set, or it outputs all but finitely many elements of the set. It can't be wishy-washy. It can't output half of them. And the existence of cohesive sets is a fairly straightforward construction. It was done by Myhill in the 1950s, although it was later improved by Friedberg, and you can make a cohesive set pi1 that is maximal. And given a cohesive set, we can form an effective ultrafilter. So it's the set of all sets of natural numbers such that all but finitely many elements in the cohesive set are in the set. And so this is an effective analog of the classical notion of an ultrafilter. And then using this effective ultrapower filter, we can do a computability-theoretic analog of the ultrapower. So we start off not with an arbitrary structure, but with a computable structure. We construct a cohesive set, and a cohesive set can quote-unquote be constructed, so its existence is provable in ZF without choice, and it's not computable or computably enumerable, but it's co-CE, at least its complement is computably enumerable. And then we fix n as our index set rather than having an arbitrary index set. And then we construct not the set of all possible functions from the index set to the structure, but we just consider the partial computable functions from the naturals to the structure, whose domain is large in the sense of the effective ultrafilter. And then we do the rest in the same way as the ultrapower. So we have an equivalence relation defined by the set of indices being large in the sense of the cohesive set. And then we define the quotient of the Cartesian power, or the computable Cartesian power, over the equivalence relation in the same way. And then we don't have Wosch's theorem, we don't get elementary equivalence, but we get what's known as Dimitrov's theorem, which says that the cohesive power of the structure is a model of at least the AE and EA sentences that true of the original structure. So it's not full elementary equivalence, but it's equivalence up to some level, and you can actually extend that equivalence if the structure has some level of decidability. And so the list of structures for which ultrapowers have been studied is all of them. Literally, I don't know of a structure that someone hasn't taken an ultrapower of. But effective ultrapowers, cohesive powers, there's far fewer structures for which they've been studied. So the first structure a cohesive power was taken of was the model of arithmetic by Pfefferman, Scott, and Tenenbaum, later written up by Lerman. So this is before cohesive powers were even formally defined by Roman Dimitrov. Pfefferman, Scott, and Tenenbaum did what we would today call a cohesive power construction. And then cohesive powers of computable linear orders like N and Q were studied by Dimitrov, Harizanov, Morozov, Schaefer, Siskova, and Vatev. And then the cohesive power of the field of rationals was studied by Dimitrov, Harizanov, Miller, and Murad. So this is a far smaller list than what's been studied for classical ultrapowers. But there has been some improvement. So Valentina Harizanov and I have studied cohesive powers for several more structures, including equivalence structures, injection structures, 2-to-1 structures, 0-to-1 structures, partial injection structures, strongly locally finite graphs, and algebraic number fields. And so today I'm just going to talk about 3 of those structures: injection structures, strongly locally finite graphs, and algebraic number fields. And so in some cases, we find that the cohesive power is isomorphic to the original structure. In other cases, we find that it's at least elementarily equivalent. But in still other cases, we find that it's not even elementarily equivalent, that it's a far wilder and more interesting object. So let's discuss these various examples. So first of all, just any questions on the general concept of cohesive powers? Okay, so the first kind of structure I'd like to talk to you guys about is injection structures. So an injection structure is a set endowed with an injective function, and then we can define orbits of these things. So orbits are basically connected components. If you view a set with a injective function as a graph, these are the connected components of the graph. So the orbit of x is the set of all y, such that x is n many steps away from y, or y is n many steps away from x by repeated application of the function. And there are 3 different types of orbits for injection structures. So there are cycles, then there are omega orbits, so they have order type omega, and then there are z orbits, so these are things that have order type of the integers. And Kisamiev defined a notion of character. His notion of character was about abelian p groups, but it has since been generalized to other kinds of structures, in particular to injection structures. So the character of an injection structure is the set of all ordered pairs k comma n, such that A has at least n cycles of size k. So this is a sort of set that characterizes the finite part of the structure. And this allows us to characterize the isomorphism types of countable injection structures, at least. So 2 countable injection structures have the same isomorphism type if they have the same character, the same number of omega orbits, and the same number of z orbits. And so if we take the cohesive power of an injection structure, first of all, it's easy to show that it too is an injection structure, because what does it mean to be an injection structure? It means that you satisfy the sentence that for all x and all y, f of x equals f of y implies x equals y. And this is a for all sentence, And so by Dimitrov's theorem, it's preserved in the cohesive power. So the cohesive power also satisfies the same sentence, but that's exactly what it means to be an injection structure. So the cohesive power is also an injection structure. And it's easy to show that the cohesive power preserves character and omega orbits. So character is very easily definable, and omega orbits, I have the definition here. We can say that there are at least n omega orbits in an injection structure, if and only if this sentence is true. So there are elements x1 through xn such that for all y, first of all, these xi's aren't equal to one another, and second of all, each of these xi's are not in the range of f, because that's what omega orbits are like. The beginning of an omega orbit is not in the range of the injective function. So because there being n omega orbits, at least n omega orbits, is an EA sentence, it's preserved in the cohesive power, and so the cohesive power needs to have the same number of omega orbits as the original structure. And by similar kinds of arguments involving Dimitrov's theorem, you can also show that the character also has to be the same.
How do these equations distinguish between omega orbits and z?
That's a good question. So z orbits, every element in a z orbit is in the range of the injective function. So whereas the omega orbits, the first element in the omega orbit is not in the range.
Is that on your formula?
Yeah, so for all y, xi is not equal to f of y. Okay. The character, yeah. So it's the set of all ordered pairs k comma n such that A has at least n cycles of size k. So it basically characterizes the finite portion of the structure, all the k cycles. Okay, so it's easy to show that the character is preserved, and I showed right here that the omega orbits are preserved. So all that's left is the z orbits, and so I have a chart showing the situation with the z orbits. So if you have bounded cycle size and 0 infinite orbits, then the cohesive power has 0 z orbits. On the other hand, if there's at least one infinite orbit in the original structure, or the cycles are of unbounded size, in either case, the cohesive power has infinitely many z orbits. And so putting that together with the results in the previous slide, that the cohesive power and the number of omega orbits are preserved, this characterizes the cohesive powers of injection structure up to isomorphism. Yeah, so it's a little bit confusing table. So the rows and columns talk about the properties of the original structure, and the interior talks about the properties of the cohesive power. So the bounded cycle size, if the original structure has bounded cycle size and the number of infinite, and there are 0 infinite orbits in the original structure, then there are 0 z orbits in the cohesive power. Whereas if either one of those two statements is false, then there are infinitely many z orbits in the cohesive power.
The table is just showing the possible set, but the conclusions are all only in the theorem. Is that what you're saying?
Yes, well, no, the interior of the table is saying the same thing as the theorem below. So the table and the words are saying the same thing for, I guess, visual learners versus verbal learners. But yeah, so okay, so that is injection structures. So any other questions on injection structures? Okay, so that was the first. That's one kind of structure that we.
Yeah, I have a question.
Yeah.
if you take two different cohesive sets, are the ultrapowers isomorphic even if you're not isomorphic to the original A?
So that's a good question. So if you take different cohesive sets, there are kinds of structures where the choice of cohesive set makes a big difference for the isomorphism type of the cohesive power. But it happens to be the case that for injection structures in particular, it doesn't make a difference. But other kinds of structures, it does make a difference. But then if two cohesive sets are can be related by a computable permutation, then their cohesive powers are isomorphic. So there are various results about varying the cohesive set and the resultant cohesive power. Any other questions on the cohesive powers of injection?
What is the cardinality of this cohesive power?
Cohesive powers, to be clear, they're always countable because we're taking a computable power. So we're taking the set of all partial computable functions, so it's always countable. So that's a very nice advantage of cohesive powers over ultrapowers. Like you're working with like a nice n over here, and suddenly you take an ultrapower, and suddenly you have this massive uncountable object. So this is a distinct advantage of the cohesive power construction. Any other questions on injection structures? So the second structure I wanted to talk about is undirected graphs, specifically strongly locally finite graphs. So just an overview of some graph theory terminology. So an undirected graph, at least for a logician, is a set endowed with a symmetric binary relation. A graph theorist might quibble, but that's what we think of as a graph, and the degree of a vertex in an undirected graph is the number of vertices it's adjacent to, and the disjoint union of two graphs is where you take two graphs and you don't have any edges between them, as opposed to the other kind of union where you could have edges connecting the two graphs. And then an undirected graph is locally finite if all its vertices have finite degree, and then it's strongly locally finite if all its connected components are finite. So these are two different notions in graph theory, locally finite and strongly locally finite. And so the first thing to say is that the cohesive power of a graph is a graph, because what does it mean to be a graph? It means that you satisfy the sentence that for all x and for all y, x is adjacent to y implies y is adjacent to x. So this is a for all sentence, and so it's preserved by Dimitrov's theorem, and so the cohesive power satisfies the same property, and so it is also an undirected graph. And then we were able to prove a universal embeddability result, that if you take any computable graph, there exists a computable strongly locally finite graph into which it embeds, into whose cohesive power it embeds. So you can think about the strongly locally finite graphs as like a basis, and all the computable graphs as a vector space. And so these strongly locally finite graphs, in a sense, generate all the other graphs via the cohesive power operation. So we were able to prove this universal embeddability result. And then we were also, the one problem with this result is that it's not a disjoint embedding. That is, it's a union of G union H, but that union might have edges connecting the G and the H, and so that's suboptimal. But then we were also able to prove a disjoint embeddability result, that if the original graph is locally finite, then you can embed it in a disjoint way into the cohesive power of some strongly locally finite graph. Okay, so any questions on the cohesive powers of strongly locally finite graphs? Okay, so now it's time for what most of you would actually be interested in, the cohesive powers of algebraic number fields. So we start off with this, the famous result of Königsmann that Z is universally definable in Q, and thus N is EA definable in Q. And so using this result, Dimitrov, Harizonov, Miller, and Murad showed that the cohesive power of Z is for all definable in the cohesive power of Q. The cohesive power of N is there exists definable in the cohesive power of Z, and the cohesive power of N is EA definable in the cohesive power of Q. And so this all depends very essentially on the low-level definabilities, because if the definabilities were too high, then Dimitrov's theorem wouldn't apply. And so it's a great testament to the achievements of number theorists and others that they're able to come up with these definabilities that are sufficiently low to make these cohesive power constructions possible. Hirschfeld showed that N there exists for all definable in the cohesive power of N. This is a result, again, from the prehistory of cohesive powers, much like Pfefferman, Scott, Tenenbaum, who showed that there is a for all there exists for all sentence, sigma, which is true of the naturals, but is not true of the cohesive power of the naturals, meaning the cohesive power of the naturals is not actually a model of arithmetic. It's not a model of the theory of N. And Dimitrov, Harizonov, Miller, and Marad used that to show that the cohesive power of Q is not a model of the theory of Q. So this is a concrete example where the cohesive power of a field is not elementarily equivalent to the original field. And so that raises a question: if the cohesive power of Q is not a model of the theory of Q, what is it a model of? Is it a model of some fragment of the theory of Q? Well, to answer that, let's consider what the nature of the field of rational numbers is. So this is a basic theorem in abstract algebra dressed up as a theorem of second-order model theory. So the field Q is the unique model up to isomorphism of the second-order theory consisting of the field axioms of the form 1 plus 1 plus 1 n times does not equal 0 for any number of 1s, and this long axiom that says for all sets X, if 0 is an X and 1 is an X and X is closed under addition and multiplication and additive inverses and multiplicative inverses, then everything is contained in X. So Q is this is a categorical second-order axiomatization of the field Q, and so this sounds like some fancy theorem in second-order model theory, but it's really just saying that Q is up to isomorphism the unique field of characteristic 0 with no proper subfields. In other words, it's a prime field. So it's just a dressed-up version of a very simple statement. And so that naturally lends plausibility to making a first-order theory as follows: by taking that second-order axiom and replacing it with a first-order axiom schema that says the same thing for any formula phi. If phi of 0 and phi of 1 and phi is closed under addition and multiplication and additive inverses and multiplicative inverses, then it contains everything. And so this process of first-orderification of categorical pi-1-1 second-order theories is how we arrived historically at a great many first-order theories. So as...
maybe it doesn't matter. You're only demanding this for, I guess, parameter-free phi.
Yeah, parameter-free, yeah. Okay, so this process of first-orderification of a categorical pi-1-1 second-order theory is how we arrived at a great many first-order theories historically. So as an example of that, there is second-order piano arithmetic consisting of these axioms for successor, addition, and multiplication, but also the second-order induction axiom. And then what we call PA, first-order piano arithmetic, was obtained by replacing the second-order axiom with a first-order axiom schema thereby forming a natural computably enumerable fragment of theory of n, because the theory of n is, of course, not CE, but this is at least a natural CE fragment of the theory of n. And by the way, the second order axiomatization is categorical. It has a unique model up to isomorphism, which is n. So this is an example of the same process. Another example of the same process is the second order theory of Dedekind complete ordered fields. So you take the ordered field axioms and you add the second order Dedekind completeness axiom. So every bounded set has a least upper bound. So that's a pi11 second order axiom, and that too is a categorical axiomatization. It has a unique model up to isomorphism, namely the field of real numbers, the ordered field of real numbers. And then in the same way, a first order theory was formed, the theory of real closed fields, by replacing the second order induction axiom with the corresponding first order axiom schema, which actually turns out to be a complete recursive axiomatization of the theory of R, as Tarski showed 100 years ago. And then finally, a more controversial example, you could say, is Ernst Zermelo showed in the early 1900s that ZFC2, the second order version of axiomatic set theory with a second order axiom of replacement, is what we might call proper class categorical. So it's not an actual categorical pi11 second order axiomatization of V, but it is a proper class categorical second order axiomatization of V, in the sense that this theory might have some set-sized models of the form V sub kappa for inaccessible cardinals kappa, but maybe no inaccessible cardinals exist, I don't know. But whether they do or not, there's only one proper class-sized model of this theory up to isomorphism, namely V. So there's this gives a proper class categorical axiomatization of V, and then the various axiomatic set theories like Z and ZF and ZFC were all obtained by first orderifying the second order, not induction axiom, second order axiom of replacement with the corresponding axiom schema, resulting in, I dare say, a natural computably enumerable fragment of the theory of V, although whether a theory of V even exists is, I suppose, infinitely philosophically controversial. Any questions on that? Okay, so the thing is that there are people in this world who believe in a mathematical universe like myself, and there are other people who believe in a mathematical multiverse. There are like some worlds where the axiom of choice is true, or there are some worlds where there are infinitely many inaccessible cardinals, and there are all these various competing worlds which are all equally self-consistent, and there's no truth value to the statement that the continuum hypothesis is true or false. So there are those kinds of people that you might call relativists, and then there are other people who think either these large cardinals exist or they don't. The continuum hypothesis is either true or it's false. And so for those people, the theory of V is a very concrete set of natural numbers, not one that we can get our hands on, but somehow it platonically exists somewhere up there, somewhere above the ceiling. But so there are some people like that, and there are other people who believe in a wild multiverse. And so this is a very active area of controversy among set theorists and philosophers and many other kinds of people. But yeah.
So in ZFC2, is continuous hypothesis true?
Sorry, what?
So in ZFC2, is the continuous hypothesis true?
I guarantee you that if it's true, then it's true. So the second order logic with standard semantics is not does not have a recursive deductive system. So if you could non-computably deduce it, then it's true. If you cannot non-computably deduce it, then it's false. But which of those two you can do. If you hand me an oracle for certain non-computable sets, I'd be able to answer all your questions, but I think those are hard to come by. So any other questions? Okay, so I hope this justifies this process of first orderification of the categorical pi1,1 second order theory of rationals. We first orderify it by replacing that second order axiom with this first order axiom schema. So this is sort of a natural CE fragment of the non-CE first order theory of rationals. And the models of this theory are exactly the, so as I said, it's a proper subset of the theory of rationals because the n is definable in Q, and so Gödel's incompleteness theorem implies that the theory of Q is non-CE, so T is a proper subset of the theory of Q, and the models of T are the fields of characteristic 0, which have no proper subfields which are definable without parameters. So there are many, many such fields, and it's actually an interesting question which kinds of fields have no definable proper subfields. There are apparently a great many of them, but I'm not an expert. But regardless, the cohesive power of Q we found is not even a model of this theory of T because it does have definable proper subfields. So not only is it not a model of the elementary theory of Q, it's not even a model of this natural fragment of the theory of Q. And so how do we show that? Well, n is first order definable in the cohesive power of Q. So basically we use the definitions of n and the cohesive power of n and the cohesive power of n and the cohesive power of Q to get a first order definition of n and the cohesive power of Q. And so if we let phi be a formula defining n and the cohesive power of Q, then it's very easy to define Q in the cohesive power of Q. We just need to say there exist natural numbers m, n, and y, such that phi of m, that is n is a natural number, and phi of n, so n is a natural number, and ny equals 1, that is y is equal to 1 over n, and either x equals my, which means x equals m over n, or x plus my equals 0, which means that x equals negative m over n. So this is a first order definition of Q in the cohesive power of Q. And so that means that Q is a definable proper subfield of the cohesive power of Q, and that too definable without parameters. And that means that the cohesive power of Q is not a model of this theory T that we define. So this is a testament to just how far the cohesive power of Q, the theory of the cohesive power of Q, differs from the theory of Q. So, any questions on that? Okay. So then, after that, we studied algebraic number fields, that is, finite extensions of Q. And we have the ring O sub k, the ring of all roots of monic polynomials in K. And we have various results, including Jennifer Park's result that if K is an algebraic number field, then O sub k is for all definable in K. And we have the result of Koymans and Pagano, and independently Alpoge, Bargava, Ho, and Schnittman. And then we have a third person, David Zuina. Yeah, so 3 different people, all within the course of, I don't know, 6 or 8 months, came up with this result that if K is an algebraic number field, then Z is there exists for definable in O sub k. And so this made our life much easier, because before, to state these results about the cohesive powers of algebraic number fields, we would have to say, if the weak Tate-Shafarevich conjecture is true, then such and such, whereas now we can state it unconditionally. So we have a theorem that if K is an algebraic number field, then the cohesive power of n is there exists definable in the cohesive power of the number field. And as a corollary of that, using the same kinds of arguments that are used to show that the cohesive power of Q is not elementarily equivalent to Q, we can show that any given algebraic number field is not elementarily equivalent to its cohesive power. So, any questions on that? Okay, and so finally we addressed a question of Dimitrov pertaining to Galois groups of these cohesive powers. So he had a general conjecture concerning the Galois groups of cohesive products, but in the special case of cohesive powers, we were able to answer it. So if K is a number field, then aught of the cohesive power of K over the cohesive power of Q is isomorphic to aught of K over Q, which is actually the same, is isomorphic to the cohesive power of aught of K over Q, because it's easy to show that the cohesive power of a finite structure is isomorphic to the original structure. So aught of cohesive power of K over the cohesive power of Q is isomorphic to aught of the cohesive, is isomorphic to the cohesive power of aught of K over Q. And in particular, if K is a Galois extension of Q, then the cohesive power is a Galois extension of the cohesive power of Q. And thus, we're justified in using the terminology of Galois theory. So we can say that the Galois group of the cohesive power of K over the cohesive power of Q is isomorphic to Gal of K over Q, which is again isomorphic to the cohesive power of Gal of K over Q. So the Galois group of the cohesive power is the cohesive power of the Galois group, at least in the context of algebraic number fields.
So can you improve the theorem to say that the cohesive power of K is just a compositum of K and the cohesive power of Q? It seems like it almost is the
Yeah, that is a true statement, yeah.
So, okay. So
Yeah.
That immediately implies...
Yeah, and this is how we prove this theorem, yeah.
Oh, okay.
Yeah.
It seems like that's more direct
Yeah.
thing to say.
Yeah, it's just that this was answering a conjecture, so,
Okay.
yeah.
So the other guy asked the wrong question.
Well, he asked a more complicated question, of which this is a special case, so. Okay, so any other questions on the Galois group stuff? Let's see. So, the natural follow-up is this is all about finite extensions of Q, that is, algebraic number fields. But then there is the natural question of what about infinite algebraic extensions, and we do have some results, but to make substantially more progress on the cohesive powers of infinite algebraic extensions of Q, we need more definability results. So it is known that Z is, there exists definable in the field of algebraic real numbers. And it is known that Z is not definable in most infinite algebraic extensions of Q, where most is in a topological sense involving co-meager sets and not in a measure-theoretic sense. But regardless, these are just very small examples. So in the Harvard DDC workshop, I made an offer of 1 meal at a South Indian restaurant for every example or class of examples of infinite algebraic extensions of Q for which Z is either for all or there exists definable. I had to include that proviso example or class of examples because if someone found a class of infinite examples, they didn't want to go bankrupt. So on that note, thank you.